Our next speaker is an industry veteran. For many years, he ran data management products at Google Cloud, which includes BigQuery. He's also an early investor in DuckDB, or I guess the Mother Duck startup. And so if you want to talk to him about trends in data management, particularly now in this space, as many of you have been following the rise of vector databases, he's a great resource for these topics. And given that this is a conference focused on knowledge bases and knowledge sources, I think it's quite appropriate that one of our first talks will be on the kind of intersection of large language models and knowledge graphs. So please welcome Sudhir Hasbe, Head of Product at Neo4J.
Thank you, Ben. Hello, everyone. It's super hard to follow a session that has great content. It has a demo and music. Like, I don't know how I'm going to beat that one. Music is hard to beat, right? So I think that's the key thing. So as Ben mentioned, I am Chief Product Officer at Neo4J now. Have been in this data space for a long time. But before I get onto the main topic, I think Christopher's session was really amazing. And the two things that stuck by me when he was talking about owning a model versus renting a model and large versus small, we have been hearing a lot of feedback from our customer base, especially developers, on how can they get started more easily, more quickly, building applications with GenAI stack. And just last week, we announced a GenAI stack deployment that was possible to go deploy on your desktop. And it includes Neo4J, of course, because we were involved. But other than that, we have LangChain, we have Ollama, which is a technology company that builds smaller models that you can deploy and customize them. And with Docker, where you can, with Docker desktop, with one-click deployment, you can get the whole stack and start developing. So I think I completely agree, having talked to many, many customers over the last year, and then even before that, when I was at Google, last 6 years, I've worked with hundreds of customers on various data management problems and all. And I think it's imperative that enterprises are skeptical of leveraging or giving all of their data up into one of the cloud services that they may not trust yet and all that. And so the question is, how do we enable organizations to innovate in both frameworks, wherein you can use your own models that are custom to what you want to do. You want to use the knowledge internally built up and also leverage large language models where appropriate. So with that, I think as I said, right, I have worked with hundreds of customers over the last few years, like, pretty deeply from large retailers to, like, largest of the manufacturers in the world. And one thing, it's pretty clear, the world is changing and it's getting more and more connected. Think about, in just last 3 years, COVID, like one pandemic comes in, the whole world shuts down, everything gets impacted. Think about, not even that, like think about one city shutting down and suddenly the whole supply chain gets disrupted across the world. A chip shortage happens in one area and suddenly the whole car industry is down and it can't provide, like, updates to new cars. You can't get newer cars, so now the second-hand cars are going through the roof in pricing. And you see this, the world being more and more connected, and the world is, as that happens, of course, the data and the digital world is actually a replica of what your physical world looks like. And it represents many times what is happening in the physical world. And this is why you will see that our data platforms are becoming more and more complex. As I said, I used to work in Google and I ran BigQuery. BigQuery was one of the largest lake houses ever built. You can use Snowflake, Databricks as the other options, but we worked with customers that collected petabytes and petabytes of data. The challenge is, as that amount of data grew, it was very clear. As soon as, let's say, retailers went online, And as you started collecting more of behavioral data of users, naturally, the 700 terabyte data warehouse on-prem suddenly becomes a 30 petabyte data store in the cloud, where you get lots and lots of IoT data, you're collecting a lot of behavioral data, you're getting all the data in the world, and that is just because how the world is getting more and more connected. And I think one of the big things that I think about is, how do you go in an organization from data to insights to knowledge? And what do I mean by that, right? I think you can go to petabytes of data, and I help a lot of organizations get there. But from there, insights is just metrics. You get reports, dashboards, various things. Maybe you do some real-time insights and all that. But the next question is, how do you go from there to knowledge? How do you really go ahead and use that petabytes of data, convert it into something that is knowledge that you can use so that you can make decisions in real time with that knowledge? And especially with generative AI technology, the next question is, how do you do that in a way that it's more accessible to users? So I think going from the massive amounts of data to extracting entities and relationships gets you to graphs. But the next step from there is, how do you add semantics? How do you add ontology? How do you add knowledge that you have within your organization, what roles you have, and what is specific to your organization? And when you add that semantic, that's where actually you get to the knowledge graphs within an organization. And once you have a knowledge graph, you see various kinds of use cases that get enabled across industries, right? The most common thing we see is organizations using these things to drive customer experiences. Because what is, a lot of times you'll hear the word customer 360 or product 360. What is a customer 360, product 360 in an organization? It's just a relationship of that product, the customer, with every other entity, the behavior, how many times it was reviewed, what information was added. It's actually a graph representation of all of that together. And if you have that accessible in a single real-time system, you can make real-time decisions, and you provide real-time offers, real-time experiences, and all. Similarly, if you look at the second area around anomaly detection. What is anomaly detection? Real-time fraud is a kind of an anomaly detection. It's basically when you know what transactions have happened, what events have happened, what are the correlated events historically with it, and how do you use those events to detect an anomaly that happens next time. Or supply chain resilience. We'll talk more about one of our customers that has whole supply chain digital twin that they use to go ahead and do supply chain resilience and use cases that come out of it. But it is all about understanding which suppliers are sending products from which areas that forms the whole supply chain for the product that you're building, and then product that you're shipping to different areas across the supply chain. Similarly, drug discovery, like National Institute of Health, uses knowledge graphs to go ahead and keep track of every drug discovery, from every enzyme, every molecule that they have used for different kinds of experiments. Every experiment is stored. And so they were telling us when basically COVID came along and they started doing experimentation, they could negate many, many possibilities of medicines upfront. It took roughly 20 hours to run all the experiments in high throughput labs. The only thing was it took another 9 months to make sure that it's safe and people could use it in real world. But actually, the mechanism of using high throughput drug discovery technology with knowledge graphs allows you to automatically figure out what the next set of options looks like and what kind of medication can be figured out. And then finally, as I said, the best way to think about knowledge graphs is it's basically a digital twin of your physical world. And your physical world is absolutely going to be pretty complex. You can't put physical world in rows and columns. Of course, you can put any data in rows and columns. I did that for many, many years of my life. But if you really look at it, physical world is more complex. It's more connected than a rows and columns-based system. So what knowledge graphs allow you to do is build that kind of a connected data model that allows you to use that in different use cases. So if you think about a transaction graph, a transaction is not a single event. It is a collection of information that goes with an individual transaction that makes it more relevant for everybody. If you're looking at consumer graph, As I said, it is about the consumer, the product, the relationships, the relationship of the consumer with other consumers, the product with other products, what products go together, and that is the complexity of all of the graph that kicks in. Similarly, parts graph. We'll talk another example later on about how one of our defense contractor organizations is using the parts knowledge graph that they've built and how they're using generative AI along with that to make it easily accessible and all. But parts graph finally is a multi-dimensional hierarchical structure where a single mission or a single aircraft or a single car, when it gets built, the number of components that go into it is pretty complex, and you have to know what relationship exists between each of these components and all. And similarly, you can take a digital twin, and that will be a pretty complex graph kind of a structure for any organization. And so why knowledge graphs? Like, what kind of questions can you answer? Of course, you can, as I said, you can represent anything in rows and columns. The problem is it doesn't allow you to answer really complex questions within organizations. Like simple questions that you may have is, what is an anomaly? Like in fraud detection case, is this transaction a fraudulent transaction? Is in a regular IoT environment, is this event that came right now, is an anomalous event or is it a regular event? Like if you want to detect maintenance issues and all, you want to be able to figure out what went wrong. And you can easily do that when you have knowledge graphs in place because they provide various techniques and technologies to go ahead and run algorithms so that you can figure that out. Similarly, if you want to know what is unusual, like a particular part has been connected to 3 different products, and normally that shouldn't be the case. It can easily detect it, it can identify it. And also what comes next. In this example, it is if some user likes a particular sport, they have purchased a specific jersey, they're most likely going to be a fan of that particular player that is there. And those kind of hidden relationships are very hard to find when you don't have a graph kind of a model and if you don't have knowledge graphs in place. And then as I said, once you have that, it becomes much easier. There are like, I don't know, 50 to 70 plus algorithms that you can run to go ahead and identify all of these different kinds of problem-solving techniques. Whether it's like path finding, what is the shortest path to go from, in supply chain case, like how do I move something easily from point A to point B without having to go through a large network. You can do centrality, that gives you like what's the most important entity, what's the most important part that you should worry about within your whole environment, which portion of your equipment is the most critical one, that failure of that can have a failure downstream into the whole equipment. Things like that you can go do very easily. Community detections, what are the communities of areas that you need to focus on? There are various machine learning things, similarity, algorithms and all. And more importantly, one of the things that knowledge graphs also allow you to do is convert a structured data, which is what a graph is, into an vectorized information. Those are what we call them node embeddings. There are edge embeddings. You can take a relationship and everything that goes with it and convert it into an embedding. And now you have a vectorized information, not about the user and their properties, or not about that entity, but that entity's relationship with everything around it. And all the buzz that you have heard about vectors and what can vectors do with large language models, imagine all of that similarity searches and scale you can do it, but now you can do it on all the knowledge graph information that you have, which is that entity, all its relationships and all. So pretty powerful stuff that you can do. So with that, that was just a primer on knowledge graphs, where are they being used, what are the different kinds of scenarios, like some basics on knowledge graphs. Let's jump onto generative AI. I'm not going to talk about what it is not. We've already discussed a few of those concepts before, but it is everywhere. I think the funniest thing is I was coming down here in an Uber yesterday, and I was talking to the Uber driver. I'm like, I'm here for a conference. I'm going to talk about this thing. And he suddenly is like excited about ChatGPT, and he started telling me about everything he knows about it. Like, the funny thing is everybody is an expert in ChatGPT and large language models now. So the way I look at it as a product person, though, is where is the investment going into? Like, a lot of times buzz happens and it comes and goes, but it's because it's at the edges of the technology, and some of them become successful, some of them not. But when I look at investments in Google, And they're embedding this technology in search and in workspace and in the core like development experience in Google Cloud. When I look at Microsoft and when I look at it and say, they're putting it in Office, like Office and search are the sacred cows of the large companies, right? You don't mess with it. Like historically, you're like, do not touch that one and do not touch Windows and all that. I used to be at Microsoft too, by the way. So those are the things that are most important pieces of technology. And when these companies go all in into that, that means, yes, there is going to be challenges and there are going to be problems. And of course, we are at the mile 1 of a marathon. Like I don't think we have solved all problems, and we'll talk more about it, and we'll solve them as they come along. But when everybody invests heavily in a set of technology, the pace of innovation goes higher and higher and higher. So you will see a lot of these problems as we detect them. How do you go ahead and make large language models answer right questions? Okay, you can have agents. Okay, what do we do there? So I think we will get better and better in that. So a lot of things I will tell you from here on are in the mile 1 of what we are seeing organizations do with the technology, how knowledge graphs and large language models are coming together. Of course, large language models were built to predict what is the next word most likely going to be in a sentence. If you read the Transformers paper, it will tell you exactly how the whole technology works, and it's basically an ability to generate information, right? Like accuracy is not the goal. The goal is to actually go ahead and generate content. That's what the whole idea of the technology was. And this is actually a real example of somebody asking, what is the world record of crossing the English Channel entirely on foot? And it has a very good answer to the problem. I don't know who the person was who was completing the English Channel on foot, but I'm super impressed. And also, if you look at it, what are the key challenges with large language models, right? First of all, it has no domain knowledge. Like, all of you have a lot of intelligence, IP within your organization, and large language model trained on public information is not going to have that. So of course, when it doesn't have information, and this is the thing I like Christopher's earlier session when he was talking about, sparse data versus massive amounts of data across different worlds, physical world versus digital world. The biggest challenge is in physical world, if you have sparse data, that's exactly the time large language models are going to make up things more. Because when you have massive amounts of data, they're most likely going to be right because they have construct of what happened before. It's when you don't have enough data is when they're going to make up stuff. And so of course, that's a big problem. Size of fine-tuning is a big problem on these models. The other thing is, can you verify? The best thing, this was in the context of a completely different thing around data quality, and I had a conversation a while back with a key leader at Spotify, and his thing was, you guys need to solve my data quality problem. And I asked him, what's the problem? It's like 10 to 20% of my data is really bad data. The only problem is I don't know which 10, 20% it is. It's the same thing with large language models. If your 20% of your, 10% of your answers are wrong, you can't trust the remaining 90% because now you're completely messed up in what is right, what is wrong, what is hallucination, what is not. I think that becomes the fundamental problem in the whole technology. And then that's the reason why you get all of these. So if you compare it to Parrot, this is the best thing I've seen on internet, I guess. So I had to add it. So it's like, can you learn random sentences? Yeah, a Parrot can do it. Of course, ChatGPT does it. Talks like a person, doesn't really understand what it's saying. Yeah, makes sense. Occasionally speaks absolute nonsense. Of course, that is true. But is it as cute as a parrot, as a bird? No. So that's the only thing. So I think Parrot wins compared to large language models. Okay, jokes apart. So how do we make this technology work in real life? What is the real way of implementing it? What are people doing with it? I think about it as left brain, right brain problem, right? We went to school, we went to the English class. The reason for going to English class was we learned how to create new content. Like we learned Shakespeare, we learned how people had done it. You could create newer poems, newer content. That's what the one side of equation is. And then you went to math and science class to learn about facts and knowledge and how do you go ahead and be factually correct. And when you bring these two things together, that's when the power happens. And I think That's exactly what we need to think about. Separation of concerns about what you're using which technology for is an important thing to think about. And this is where I think bringing these two technologies together helps organizations leverage or get the most benefit out of this technology. And so with that in case, there are 3 key use cases that we are seeing that most of our customers are using, and we'll talk specifically about them. One is using large language models where they're really good at, language constructs. We'll talk more about that. Of course, the retrieval augmented generation, everybody must have heard about RAGs, and this is the most popular pattern that's coming up. And we'll talk about where this is relevant, where do vector databases play a role in this, and how vector data types will play a role and all that. And finally, knowledge graph construction. There is tons and tons of unstructured data sitting within organizations. How do you convert that into knowledge graphs and use that for more better decision making is an important aspect to it. So one of the examples here is we're working with various customers, and this is the most common one because this is the easiest one for developers to get started with. It's historically, if you think about it, if you had a recall on your car or recall on a product, you will get an email. Most likely, it may be filtered to people that have bought that car before, but there is no personalized message or information in it. But imagine if there's a personalized message where, when did the last service happen on the car? What are the specific recalls that have been already fixed? Which are pending? And how do you go ahead and automatically generate that content and send it? That becomes way more compelling for me who is receiving things. Because otherwise, I keep ignoring these emails that come to me from a particular dealership or something like that. So we are seeing a lot of use cases where, just using knowledge graph as your knowledge base, taking the content out of it. Historically, what was a message that was going out, which was mostly non-personalized or templatized is a better way of saying it. You have a template, you put the name of the user and then send an email out. That is fundamentally changing to be more personalized with more context, what the person has done, where have they been, and all of that stuff. So I think in that case, you have the application going to knowledge graph, picking up the right context, creating a prompt, sending it to large language model APIs, and then generating a response, which can be an email, which can be a targeted message, it can be a messenger message that goes out, or just an application notification that goes out and all that. So that's one very common pattern that we see. The second big one, and I think this was also what Christopher was talking about, leveraging natural language to access knowledge within enterprises is the most fundamental thing every CIO talks about. I actually, in my last job, I was trying to do this with data Q&A. It was one of my ideas in 2018-19 on natural language access to data. It didn't succeed. There was a lot of technology problems. But with large language models, now I think there is more hope to go ahead and make that happen. And what we see with knowledge graphs coming together, I think with the large language models, this is really compelling. And this is a good example. This is J&J. They presented at our previous conferences about what they do. So they have a whole supply chain resilience graph. They basically use a knowledge graph that has end-to-end supply chain replica as a digital twin. And then within that, they can say, there was a hurricane in Florida a few weeks back, and if that is the case, they can say, if that happens, what's the impact of all the drugs that need to be delivered to all the different pharmacies within different parts of US? And if that is the case, then how many, if this is out for 3 days, what kind of inventory do I need to hold? The other example that they have is, are there products being supplied by a single supplier in any part of the world? You want to know what happens if that supplier is not available. What kind of things do we need? You can go ahead and have multiple suppliers supplying, but that may not be always the best way of handling it. Holding more inventory may be a different thing. So those are the kinds of things they use the knowledge graph for. But the problem is it's only accessible to 300 people that know how to use a graph. They know how to go ahead and leverage graph technology with graph analytics and visual tooling and all. And their thing is there are thousands of people running around. That's 140,000 plus employees within that organization. How do you make it accessible to thousands of people than just few hundred people? And this is where they are using natural language experience running on top of knowledge graph. And in this case, what happens is it's basically user basically asks a question. You go ahead and convert that into a prompt. That prompt basically is sent to LLM API, and which converts it into a cipher query. Cipher query is just a graph query language, so you basically convert that into a graph query, send it to the knowledge graph, extract the exact information, and then from there, you send it to the large language model to convert it into an English translation, and then go ahead and represent it. The advantage of this is, if you didn't find that information in knowledge graph, it will tell you, I don't know the answer, rather than giving you a wrong answer. So you will always have accurate information that the user is getting in this scenario. This is a very common pattern. We see this all the time. The next example of this is even further. This is one of the defense contractors we are working with. First of all, they cannot use any of the public LLMs because they can't even get to ChatGPT. None of them, their employees. It's highly secure. The other part of the problem is all these missions have massive amounts of parts. Like, you think about a parts graph for a rocket that they're building for US defense and all that. And they're really complex environments. And they had thousands and thousands of parts documents sitting across as PDF documents everywhere in the world, in all the different locations in their secured stores and all that. But whenever a user comes in and it wants to know how to go ahead and build something or fix a particular engine or something like that, they have to find information that spans across those parts as well as the unstructured documents that are there. And what they are doing is they are now leveraging, they've converted all of their unstructured data into vectors and vectorized information, and then leveraging a dual path wherein you can go ahead and search based on either a part number, if you know it, and if you don't know the part number, you can just give description of what kind of part you're looking at, and you can do a search based on a vectorized information, which is a vector similarity search, and then get an answer for that. So basically, it's a blend of unstructured as well as structured discovery, and then all of that combined into a single application. And I think this is really interesting in other scenarios too, like one of our other customers, Klarna, is doing very similar stuff. I will go into that in a break or something to share more what they are doing. But fundamentally what it means is, by combining the ability to have a graph-like representation along with vectorized attributes and having a vector index that can optimize for searches on vector information, which can be a similarity, which is an implicit discovery, or if you know the exact entities that you're looking for and then filter them down, it highly optimizes and reduces the cost of how you're going to go ahead and run the discovery. So I think this is a very common pattern that we are seeing. The one before that, Klarna, is the same example. The defense contractor example I gave you, I think there's very similar. We are seeing lots and lots of use cases where the blending of vectors and within a knowledge graph along with the structured discovery is actually becoming really very interesting for solving various different use cases. And then, of course, when you have that, you can have an application that brings all of this together between explicit and implicit discovery. The next one I will talk about is an oil and gas company, and they basically have massive amounts of infrastructure across the globe. They have lots and lots of data, similar to the earlier one that I was talking about, defense contractor. In this case, you have lots of unstructured data sitting around within the organization. And then how do you actually convert that into knowledge so that you can consume it more easily? Having PDF documents and forcing people to read them across to understand what needs to be done is super hard, right? And historically, converting unstructured data into structured information was also hard. Like, you had to go ahead and say, in December 1903, okay, most likely that's a date, and then there is the academy, so there's another entity and all. So deciphering this was super hard. Versus large language models actually are good at doing this thing, wherein they can extract entities based on templatization, based on the prompts-based training that you can give them, and you can tell them exactly what you're looking for, and they can extract more of their knowledge. And then, as I said, the beauty is with having ability to have vectorized information of the whole document, but also extracted information into a knowledge graph, you can blend discovery, blend, making decisions across both of these data sets. And that's exactly what we are doing on that one. So the construction of knowledge graph from an unstructured data set that was there sitting across your organization is actually a pretty powerful third use case that we are seeing. And so fundamentally what it comes down to is three things. We see knowledge graphs are being used within large organizations for various use cases, from fraud detection to digital twins, whether they're supply chain, whether they are manufacturing floors, whether they are parts, a product, digital twin of a product, which is the product and it's all parts and their knowledge bases and all. So I think that's one thing pretty common across the board. Second is, grounding LLMs with enterprise data is foundational to go ahead and get value out of large language models and the technology that's available. And then finally, there are three main use cases we see in mile one. As I said, there are 25 miles to go. I run half marathons and marathons, so that's why this is closer to my heart. And in first mile, it's always easy. So the three things that we see is use the technology for what it's good at, use language skills for it. Second, ground the information back into knowledge of your enterprise. I would recommend knowledge graphs being much better representation of knowledge than any other technology that I have seen. And then finally, creating knowledge graph out of your unstructured data that's sitting all across your company, but it's not being used effectively, is the third area. So those are the three things to take away from the session, and let me pass it back to Ben and team. Thank you, everyone.
Thanks a lot, Sudhir. It was a fantastic talk.
Thank you.
I have a couple of questions. One is on extracting the knowledge graph from unstructured data.
Yeah.
How do we ensure quality?
Yeah.
Right? Because when we write documents, some of the statements may be contradictory, and the same information may be represented in multiple ways. So how do we ensure quality?
Yeah.
And the second one is having certain, say, poor quality graph inside. How do we ensure that the answer that comes out of the knowledge graph is sound?
Yeah.
Right. One is I'm asking about the data quality at the source as a knowledge graph, but having certain, say, uncertainty in the knowledge graph, how do I make sure that the extracted information is sound?
I think that's a great question, and I don't think we have solved every one of those problems in that area. But I think there are a couple of things, right? What you can do really well is if you templatize what information you're extracting, and if there is duplicative information or contradictory information coming into the templates, the ability to reject that is one thing we can do. The second thing is if you build a knowledge graph, this is what I was highlighting in the kinds of algorithms we have, wherein if you basically try to link a piece of information to two different things which is contradictory, you should be able to detect those kind of things using graph algorithms, and we should look at those techniques to figure out if we can do that. So the graph algorithms may be able to find, hey, are you saying something or connecting this particular entity to that entity and connecting it to a different entity in the same way, but it should never happen? Can we identify those? Those would be some of the techniques I would use. But I think you're absolutely right. If the source data is really confusing or inaccurate, more importantly, what you create out of it is also going to be inaccurate. So I think the focus will be more on detecting that using algorithms and what can we highlight there itself. And if we can reject it at the time of ingestion rather than later, would be a much better way of doing that. So those will be a couple of things I would think about.